Good morning. This is Mr. Osley, and I imagine you're here today because you missed out on our class activity DNA, breaking the code. Though it's sad I wasn't able to see you in person, I'm glad that you're taking your time here and now to get caught up so that when the next section comes, we can jump right in. To start, I would like to pause here and give you some time to grab what you will need. That will be your lab journal or a piece of paper in something to write with. If you don't have these items, I will accept a Microsoft Word document or Google document. So let's pause for a moment. Let's get your things in order, and then we'll continue. All right. So now that we have everything in front of us, let's begin. We'll go over a basic outline of what to expect today. So this section is based on DNA, specifically the code and data contained within DNA. We will go from the minuscule, the basic language coded inside the DNA and its nucleotides, to its codons, then its amino acids, and then finally translating those amino acids into proteins, and from there, traits that we see in living organisms. You may notice within this video that there's a few links right underneath it. The very first is a link to these very slides that you are seeing on your screen here. If you would like to follow along to be able to see some of these videos in person, feel free to access those. Secondarily, you'll notice an intro video, the very same one that's here on this screen. Do not open it yet. I'll tell you when it's ready to watch. Finally, there's the handout for today, DNA cracking the codon. I'd like you to take a moment and open that up or even print it so that you have access to everything you need. Once those are ready, unpause the video and we'll be ready to begin. I'll let you pause here. Congratulations. So now that we're ready, I would like you to open up the video link, Imitation Game trailer. Please access it from the link below and watch it to its entirety. It's quite exciting and maybe a little bit loud. Pause here, watch it, and then come back. As you saw, during World War II, the Nazi forces of Germany utilized a brutal combination of machine and ingenuity, dubbed the Enigma. The codes created by this machine were nigh unbreakable. However, it took the unique combination of brilliant minds, Alan Turing, Joanne Clark, Colonel Hugh Alexander, and John Carencross to break the code, discover a cipher, and in the end, break the Nazis' hold over Europe. 20 years after this, a new code began to emerge, one no less complex, whose cracking could uncover the very secret language of life itself. Over the course of several years, Marshall Nirenberg, Har Khorana, and Severo Ochala, along with several of their additional colleagues, cracked it. In 1966, it was official. The genetic language of DNA was cracked. It may often seem impossible. How could they do this with so little foreknowledge, little access to the technologies we may have today, and uncover such wonders? Well, though we may be standing on the shoulders of our ancestors, perhaps we might learn something, a bit of their struggles and their discoveries by following in their footsteps. Over the next few days together, we're going to delve into the secret language of DNA and crack its code. So to delve into the mysteries of DNA, we need to remember what DNA actually is. Now, you may have covered this before, but how much of it do you remember? Let's have a refresher. So on your lab journal or your paper, I would love if you would write down a section called My Memory on DNA. Once you have that written down, I want you to put everything you can recall. What is DNA? What can you remember about it, its form or function? Do you remember what nucleotides are or the base pairs? Can you list them or name them? Maybe you can only remember the base pair rule. Take a moment, pause the video, write everything down you can, and then we'll go over. Fantastic. So, as you may remember, DNA is the data holder of life, containing its information or recipes for things like organs, bones, and blood. Just like a computer program, it holds its own programming language, in this case called nucleotides, also known as base pairs. Those base pairs are adenine and thymine, or A and T, and guanine and cytosine, C and G. These base pairs are complementary. They will only dance with their partners. A always matches with T, C always matches with G. For a long time, the only thing that was known about DNA was that these base pairs matched, and little was known about its true components. However, we've actually learned its language over time. Together, we're going to build our own code and see what animal our code belongs to. As you see here in this section, I do have a few videos alternatively explaining DNA. If you have access to the slides, please take a moment and pause the video, watch them, see if maybe the different wording might help enlighten you. And when we're ready, we'll go on to the next step of our progress. Fantastic. So on your lab journal or paper, we're going to start building our own chains of DNA. 3 sets of 12 nucleotides or base pairs. Before we begin, there's a few rules. Number 1, each DNA chain must be unique. No copying them all across. I don't want all 3 to be exactly the same. And number 2, each chain must contain at least one of each of the different base pairs. So no all A's, no all T's, and then all C's. One of each at least. That'll help with variation. And in life, it's not only the spice of it, it also makes sure that we don't end up just balls of feet. Now, in addition to this, I want you to make sure that each section of DNA that you have has some room around it that we can draw in. You can draw each of the base pairs in different colors. You can see that I did in my section here. There it is. This will be important, and so that's why I have my example on my slide. Don't copy my example. It'll make it boring. All right. Take some time. Create your 3 sets of 12 nucleotides following those rules. I'm going to let you pause the video, and then we'll get right back into it. Fantastic. All right. Now, when the cell reads DNA, it doesn't do it in a solid string of code. That would take far too much time. It chunks it down into little units of 3. These units of 3 are known as codons. It makes it easier to read, and it effectively chunks the recipe down to not become one giant monstrous task. Finding this out was a huge step in understanding DNA. For us, now that we understand what we're supposed to do, it's actually a much simpler task. So what I'm going to have you do is, for each section of DNA that you have, draw a line in between each, chunking them into groups of 3. On our next page, you'll see that I've already done this and even labeled them: codon 1, codon 2, codon 3, and codon 4. Take a moment, do this, unpause. Great. So these codons that we built are the secret mini recipes that unlock some of the true potential of our DNA. Each codon is a blueprint for a chemical known as an amino acid. Now, amino acids are the building blocks of proteins, and proteins are the building blocks of life. There is a very specific purpose to DNA, however. It makes sure that the amino acids are produced in order. The order is the key to a protein. Unlike making a cake, if you put your eggs before your flour, it will drastically alter your results. So the order that our amino acids are produced is vital to creating the correct protein. This, of course, was another major hurdle until again, it took the hard development and time to crack this code. We're lucky because I've created a handout. I imagine you've already opened the handout. It is called Cracking the Code. And take a look at that front page. I would like you to take a moment, pause the video again, and read that initial paragraph, and then we'll get back to it. Great. Now, this might look a little bit intimidating, but that chart contains every combination of nucleotide possible. I've simplified it for this because I don't want you actually creating full human bodies. That'll be later. What we're going to be doing now is do a more simplified uncoding process using this handout. So now that we have our codons, we're going to match them to the different sections of that handout. You'll see that the amino acids that the codons turn into are also chunked into three-letter little sections. This is ease of use for now. Don't worry about their full names. The amino acids we're going to be focusing on are GLU or glue, LEU or lu, SER or SIR, and then ALA or ALA for short. So the way we translate this is simple. For each codon, like in the example we see here, AAG, we'll find the matching set on our handout. That will tell us what that codon matches to which of those 4 amino acids. As you can see here, AAG matched to GLU. If I were to use the codon ACA, I would look for ACA on the chart, and I would see that that codes for ALA, the amino acid. So next to each of those codons, we're going to write what amino acid it translates into. So I want to give you a moment. Take your time. If you need to rewatch this section to get a hold of what's going on, feel free to. This is important. I want you to make sure that you have the time in order to see this through. Pause the video, and I'll see you in a little bit. It might have been a little hard, seems a bit like a puzzle, but I'm glad you got through it. Now, we're almost done with our lesson for today. I want to do a recap just to make sure everything's fresh within our minds and that we have our key terms down. So today, in our video, we learned about the building blocks of DNA called nucleotides and that they're paired chemicals, a set of each known as adenine and thymine, guanine and cytosine, and they only like to pair with each other. When reading the DNA, the cell reads these in 3 nucleotide chunks called codons. And each of these codons, which makes it easier to read, translates to an amino acid, which are the building blocks of our proteins. The order of our amino acids are very important. The order can change what protein is made. Very good. At the bottom of your journal page or the paper you're using, please create a section called vocab. There, I want you to put down our 4 big terms for today: DNA, nucleotides, codons, and amino acids. For each of these terms, I want you to write down 2 things: the definition you heard me say, or even a definition you found on the internet for it. And then a definition in your own words. Creating 2 definitions for each of those can help you remember that for times to come. And that will be important for the next section and the assessment down the line. Please, when you are done, make sure you save your lab journal, save that piece of paper, or save that Word document that you made for this. That's your proof to me that you took your time. And I do not want you to lose those points. You deserve every single one for going through this with me. Sorry I can't see you now. I hope to see you soon. And I also hope you have far better days ahead. Have a wonderful day, a wonderful week, and I hope I'll be able to see you soon.